This is the 9th video lesson for Unit 5B. In this lesson, we'll be analyzing sigma and pi bonds and how do they form. Go to page 31 in the class packet. Keep in mind, this topic is not on the Chemistry Regents exam. Motivation: how many electrons are in a double bond? How many are in a single bond? There are 4 electrons in a double bond and 2 electrons in a single bond. Learning target. At the end of the lesson, I will be able to count the sigma and pi bonds in a compound. I will be able to determine the hybridization of atoms in a molecule. Homework number 9 will be based off this lesson. There will be a quiz based off PowerPoint 7, 8, and 9. Sigma and pi bonds are chemical covalent bonds. Sigma and pi bonds are formed by the overlap of atomic orbitals. Sigma bonds are formed from end-to-end overlap of the orbitals. This is the symbol sigma. In this diagram, there are 2 atoms. Each atom has an s orbital. When they bond, the s orbital will overlap end-to-end, forming a sigma bond. The electron density is concentrated between the nuclei of the bonding atoms. Here's another diagram showing sigma bond formation from different atomic orbitals overlapping end-to-end. Pi bond, on the other hand, are formed from side-to-side overlap of the orbitals. This is the symbol pi. In this diagram, there are 2 p orbitals. Each p orbital is on a different atom. When the p orbitals overlap, they overlap side to side, forming a pi bond. This represents 1 pi bond. The electron density in a pi bond is above and below the plane of the nuclei of the bonding atoms. This is a summary slide. Sigma bonds are formed from end-to-end overlap of atomic orbitals, while pi bonds are formed from side-to-side overlap of atomic orbitals. So how do we count the number of sigma bonds and pi bonds in a molecule? Single bonds only have 1 sigma bond. Double bonds have 1 sigma and 1 pi bond, as you can see in this diagram. Triple bonds have 1 sigma and 2 pi bonds, as you can see in this diagram. Keep in mind, sigma bonds are stronger than pi bonds. This is because the overlap in sigma bonds are end-to-end rather than side-to-side in pi bonds. Since double bonds have 1 sigma and 1 pi bond, they are stronger than single bond, which only has a sigma bond. Now we're going to count the number of sigma and pi bonds. Let's look at the first example. Keep in mind, single bond is only 1 sigma bond, double bond is 1 sigma and 1 pi bond, triple bond is 1 sigma and 2 pi bonds. In this molecule, there is 1, 2, 3, 4, 5, 6, 7, 8 sigma bonds and 1 pi bond from the double bond. Let's look at example 2. There is 1, 2, 3, 4, 5, 6, 7 sigma bonds, and there are 2 pi bonds. There's 1 pi bond in each of the double bonds. Learning check number 1. In pentadiene, how many sigma and pi bonds are present? Pause the video, resume as completed. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sigma bonds. And since there's 2 double bonds, there are 2 pi bonds. The answer is choice 2. Learning check number 2. Base your answer to the following question on the diatomic species below, which contains 1 sigma and 1 pi bond. Pause the video, resume as completed. 1 sigma and 1 pi bond means a double bond. By looking at the diatomic molecules here, only O2 has a double bond, so the answer is choice 2. For the practice questions, count the number of sigma and pi bonds in the following molecules. Try to do this yourself. Pause the video, resume once you want to see the answers. Here are the answers. To further analyze how covalent bonds are formed, we're going to talk about hybridization. When you see the word hybridization, you think of the word hybrid. Here's an example. Here you have a horse and a donkey. They make a mule. A mule is a hybrid of a horse and a donkey. So a hybrid is a blending or mixing of different varieties. In chemistry, hybridization is a concept of mixing atomic orbitals to form new hybrid orbitals. These new hybrid orbitals have different energies and shape. As you can see from this diagram, you have an s orbital mixing with a p orbital. These orbitals are from the same atom. When these atomic orbitals mix, they form new orbitals, called hybrid orbitals. A set of hybrid orbitals is generated by combining atomic orbitals. The number of hybrid orbitals in a set is equal to the number of atomic orbitals that were combined to produce the set. For example, here we have two atomic orbitals hybridized to form two hybrid orbitals. Hybrid orbitals are formed when atomic orbitals from a single atom combine. Hybrid orbitals are used for covalent bonding and are formed before bonding. They're not formed in isolated atoms. So here are some examples of hybrid orbitals depending on the atomic orbitals used. These diagrams should look familiar to you. They are from the VSPR theory. The type of hybrid orbitals formed depend on the electron pair geometry as predicted by the VSEPR theory. Now we're going to look at some examples on how hybridization works. The example we're going to use is carbon. What is the orbital electron configuration of carbon? If you recall, carbon has 6 electrons, so the orbital electron configuration is 1s2, 2s2, and 2p2. If you were to draw the energy diagram, it will look like this. There are 2 electrons in the 1s orbital, 2 electrons in the 2s, and there's 2 electrons in the 2p. Using Hund's rule, question 2, how many unpaired electrons are present in this configuration? Try to figure this out yourself. Pause the video, resume as completed. By looking at this diagram, there are 2 unpaired electrons in the 2p. How does carbon form 4 bonds then? By looking at this electron configuration, you would think that carbon can only form 2 bonds, but you should know that carbon forms 4 bonds, as you can see from these Lewis dot diagrams. So the question is, how does that happen? The answer is there must be hybridization of the orbitals in the valence shell. We are going to look at 3 scenarios involving carbon. The first scenario involves only single bonds, the second scenario involves a double bond, and the third scenario involves a triple bond. The first scenario we're going to look at is sp3 hybridization. It is when one s orbital and 3 p orbitals hybridize to form sp3 hybrid orbitals. So in a carbon atom, we're going to hybridize the orbitals in the 2s and 2p. How many hybrid orbitals will form if 1 2s and 3 2p orbitals mix? So since there's 4 atomic orbitals mixing, there will be 4 hybrid orbitals formed. The energies of the hybrid orbitals are between the energies of the original atomic orbitals. The 4 new 2sp3 hybrid orbitals are equivalent in energy. Once the hybrid orbitals are formed, the original atomic orbitals disappear. Let's analyze the 2sp3 notation. The 2 tells you the energy level, the sp tells you the contributing atomic orbitals, and the 3 tells you how many. So there were 3 p orbitals and 1 s orbital mixed together to form the hybrid orbitals. Now let's look at pictures of carbon before and after hybridization. Here is the nucleus, here is the 1s orbital, the 2s orbital. If you recall, s orbital is a spear shape. We are going to ignore the 1s orbital because it is not in the valence shell. The p orbital is a dumbbell shape, and there's 3 of them. So this is carbon before hybridization. Now we're going to hybridize the 2s and free 2p orbitals. So now we form 4 new hybrid orbitals. These are 2sp-free hybrid orbitals. All of the 4 2sp-free hybrid orbitals are equivalent in energy. If we were to measure the angles, this is 109.5 degrees. This is a tetrahedral shape. This hybridized carbon atom can now bond. We're going to look at an example, CH4. This is hydrogen. Hydrogen only has one electron in the 1s orbital. This carbon is going to bond with 4 hydrogen atoms. Since both carbon and hydrogen have unpaired electrons, they will bond by overlapping the hydrogen's orbital with the carbon hybridized orbitals. Since they will overlap end to end, as you will see in this diagram, 4 sigma bonds will be formed. Here are the 4 sigma bonds. They represent the 4 single bonds in CH4. The carbon is sp3 and the hydrogen is s. This is a summary slide. In sp3 hybridization, you have one s orbital and 3 p orbitals mixing together to form 4 hybrid orbitals, which gives you a tetrahedral shape. Learning check number 4, a sp2 hybrid orbital is formed by mixing what? Pause the video, resume is completed. Based off the notation, there is one s orbital and 2 p orbitals. The answer is choice 2. Next, we're going to look at sp2 hybridization. So we have one s orbital mixing with 2 p orbitals. We're going to look at this example because this carbon is sp2 hybridization. The CH bond is a sigma bond, and the double bond between the two carbon consists of a pi bond and a sigma bond. In order to get sp2 hybrid orbitals, we need to mix the 2s orbital and 2 of the 2p orbitals. How many hybrid orbitals will form if one 2s orbital and 2 2p orbitals mix? Since we started out with 3 atomic orbitals, we will get 3 hybrid orbitals. Here are the 3 2sp2 hybrid orbitals. Notice there is one 2p orbital that is unmixed, unhybridized. This unhybridized 2p orbital can form a pi bond. The 3 2sp2 hybrid orbitals can each form a sigma bond. Now we're going to look at pictures of carbon before and after hybridization. This black dot is the nucleus. This is the 1s orbital, the 2s orbital. We're going to ignore the 1s orbital because we're going to focus on the valence shell. Here are the p orbitals. So this is carbon before hybridization. In sp2 hybridization, we are going to mix the 2s orbital and 2 of the 2p orbitals. One of the 2p orbitals will not be mixed. Afterward, there are 3 2sp2 hybrid orbitals and one 2p atomic orbital that was not mixed. All 3 of the 2sp2 hybrid orbitals are equivalent. If we temporarily remove the 2p orbital, we can see that this is a trigonal planar shape with 120 degrees between each of the 2sp2 orbital. Now let's go back to this example and see how the double bond is formed. Here are the 2 carbons before they bond to form the double bond. Each CH bond represents a sigma bond. This red orbital represents the 2sp2 hybrid orbital. These blue orbitals represent the 2p. Now we're going to put the 2 carbons close together. The two sp2 hybrid orbitals from each carbon atom overlap end to end, forming a sigma bond. Now the p orbitals on each carbon atom will overlap side to side to form the pi bond. Since the two p orbitals overlap side to side, one pi bond will be formed. In summary, for sp2 hybridization, one s orbital and two p orbitals mix together to create three hybrid orbitals, which give us a trigonal planar shape. The last scenario that we're going to look at is sp hybridization. It is when one s orbital and one p orbital mix together to form two sp hybrid orbitals. We'll be looking at this example because this carbon is a sp hybridization. The CH bond consists of one sigma bond, and the CC triple bond consists of one sigma and two pi bonds. In sp hybridization, the 2s orbital will mix with one of the two p orbitals to form the hybrid orbitals. How many hybrid orbitals will form if one 2s and one 2p orbitals mix? Since we are mixing two atomic orbitals, we will get two hybrid orbitals. Here are two sp hybrid orbitals. There are two 2p orbitals that's unmixed, unhybridized. Both unhybridized 2p orbitals can each form a pi bond. The two 2sp hybrid orbitals can each form a sigma bond. Now we're going to look at pictures of carbon before and after hybridization. Here's the nucleus. Here's the 1s orbital, the 2s orbital. We're going to ignore the 1s orbital because we're going to focus on the valence shell. And here are the 2p orbitals. This is carbon before hybridization. For sp hybridization, we are going to mix a 2s orbital and one 2p orbital. After hybridization, we form two 2sp hybrid orbitals. Notice that two of the 2p orbitals remain unmixed. All the two 2sp hybrid orbitals are equivalent. If we temporarily remove the 2p orbitals, we can see that it formed a linear shape with 180 degrees between the two sp2 hybrid orbitals. Now let's go back to this example to see how the triple bond is formed. I color-coded everything. The red orbital represents the two sp hybrid orbitals. The blue and green represents different 2p orbitals on each carbon. The CH bond consists of a sigma bond. Now I'm going to put the two carbons together. The two sp hybrid orbitals from each carbon overlap end to end to form a sigma bond. There are two p orbitals on the carbon. Each one will overlap side to side with the two p orbitals of the other carbon. As a result, two pi bonds will be formed. I will first overlap the p orbitals highlighted blue. This is one pi bond. Next, I will overlap the p orbitals highlighted green. This is the second pi bond. So as you can see, the triple bond consists of two pi bonds and one sigma bond. In summary, in sp hybridization, one s orbital and one p orbital mix together to form two sp hybrid orbitals, which gives us a linear arrangement. This table summarizes the hybridization with the geometry using electron density region. Electron density region is the same as electron dense area. They represent the number of bonds and lone pairs. Use this table to identify the hybridization. Let's look at an example. CH4 has 4 electron dense areas. 1, 2, 3, 4. Therefore, This carbon is sp3 hybridization. Since this hydrogen only has one electron dense area and a hydrogen atom only has one electron, then it will be S. Typically on exams, they will only ask the central atom. Learning check number 5, the bonding orbitals on the central atom in a CF4 molecule are what? Pause the video, resume as completed. CF4 looks like this. Since carbon has 1, 2, 3, 4 electron dense area, it is sp3. Learning check number 6, which hybridization of orbitals is present in NH3? Pause the video, resume as completed. First we draw the Lewis dot diagram of NH3. There is 1, 2, 3, 4 electron dense area. Therefore, the hybridization is sp3. In this practice, label each atom's hybridization. Try to do these questions by yourself. Pause the video, resume as completed. Here are the answers. This concludes the video lesson. Remember to do the homework and quiz.